Currently, our basic atomic structure is comprised of three principal particles. And we have, the proton, we have the neutron, and we have the electron. And so as far as maybe a quick table, we could look at the particle, we could look at charge, mass, and then the relative mass. So if we start with our proton, we find the charge is positive. Find it has a mass of 1.674 times 10 to the negative 27th kilograms, and it has a relative mass of 1 AMU. I'll come back to the AMU in a second. We then have our neutron. A neutron is neutral, so there is no charge. And it weighs pretty much the same, pretty close. A little different to the proton, 1.672 times 10 to the negative 27th kilograms, and we also give that a relative mass of 1 AMU. And then lastly, we have the electron. The electron is negative, and we find a big difference in mass here, 9.1 times 10 to the negative 31st kilograms, and that would be technically 1/1800ths of an AMU. So let's get into the AMU. Basically stands for atomic mass unit. Since protons, neutrons have the same mass, they have, a relative mass of 1 AMU. This has implications. And basically, what are the implications, due to the significant difference in mass of protons, neutrons, relative to electrons. The electron does not contribute to the atom's mass. Only the protons and neutrons. So that's a big deal there as far as understanding that electrons don't contribute to the mass of a particular atom. Only the protons and the neutrons. So when we look at elements, right? We have element symbols, or a representation of the element, protons, neutrons, and our electrons. And so we tend to look at something in terms of having like X, and X is basically standing for the elemental or the elements symbol. This is a 1, 2, 3. We're going to get into 3 letter codon, right, to actually help us with what the element we're talking about. We then have atomic mass in the kind of top left portion of this representation, and we then also have our atomic number in the bottom. So again, X here stands for element symbol. For example, carbon would it be equal to C? Helium will be equal to He, etc. And then we have our atomic mass. And the atomic mass is basically the sum of the number of protons and number of neutrons. And then our atomic number is equal to the number of protons. Crucial with the atomic number is that this is, what identifies the element. Using all of these components, the atomic mass, atomic number, we can actually figure out all the individual particles for any atom of an element. So if we look at an example of this, we could look at carbon here with a C. That's what we get from the elemental symbol. We're talking about carbon. we have an atomic mass of 12. And we have an atomic number equal to 6. So what does that mean? Well, that means in terms of the atom carbon, I have 6 protons. In terms of the atomic mass, I know my number of neutrons plus my number of protons equals 12. So if I don't know my neutrons, but I do know my protons, right, that has to equal 12. So that means I have 6 neutrons as well. So that means that for this particular element, if we're looking at carbon, carbon has basically 6 protons, 6 neutrons, and 6 electrons. Remember, for an element that is neutral, the number of protons equals the number of electrons. As far as that representation goes. So that allows us to determine basically all the number of particles that are present in an element based on the idea of the elemental symbol, the atomic mass, which is the sum of protons and neutrons, as well as then the atomic number, which is the total number of protons within an element. Now, within elements, there are different forms of the elements. And so we have one form here, which is isotopes. And isotopes are atoms of the same element. That means same number of protons. With different numbers of neutrons. And so that's basically our definition of an isotope. As an example, we could look at hydrogen. If we look at hydrogen, it has 1 proton, 0 neutrons, and 1 electron based on its neutral species. If we go to a second form of hydrogen, notice that our number in terms of our atomic mass has changed. Here we actually have still one proton, but now we have one neutron and still one electron. This isotope has a common name, which is known as deuterium. Maybe you have heard of it. Maybe you've heard of the term heavy water. Heavy water is D2O or deuterium as opposed to hydrogen. So often it's given this actual other type of symbol. Technically it's still hydrogen, but deuterium is just a commonplace name. And then we get to the third form of hydrogen, where we still again have that one proton that's still identifying it as hydrogen, but now we have two neutrons and still one electron because it's neutral. This is known as tritium. And so it often has the T as far as its symbol. Tritium is radioactive. So you might have heard of tritiated water, things of that nature, especially with power plants, nuclear power plants involved. And so that's coming from that radioactive isotope of hydrogen. So all of these are the same element, hydrogen. They just have different numbers of neutrons. Another example would be, just quickly looking at carbon. So these are all carbon elements because of that elemental symbol. But while we are the same in terms of our number of protons that we get from that number 6, right, we actually differ in the number of neutrons. Here we would have 6 neutrons, while here 7 for C13, and then 8 for our C14. So that's how you can develop, the different numbers of particles that are there. In all of these cases, we would have the same number of electrons. And again, that comes from the neutral idea of the element. If we, look on the periodic table, we don't find integer masses for, elements. Meaning that if we look at the 3 isotopes of carbon, if we go to the periodic table, we will see that carbon has a mass of 12.011. So where does that come from? I mean, we have carbon and isotopes. Okay, I get you there. But these isotopes have different mass, 12, 13, and 14 in terms of carbon. But yet when I go to the periodic table, I see this, mass of 12.011. So that's our first equation. If we look at the periodic mass, for an element, we find it's really a weighted sum or a weighted, average, if you will, as far as looking at, the sum of the fraction of the isotope, and then that would be times then the mass of the isotope. So it's a summation, but we're, kind of using a percentage. Right? The fraction is basically before a percentage. And then we're just multiplying it by the mass of the isotope, right, as far as the number of our protons and neutrons is concerned. So that's how we get the periodic table mass. It actually means that even though carbon is comprised of 3 elements, well, I apologize, it's comprised of 3 isotopes, C12, C13, C14, that most of carbon actually exists as C12. And that's because our periodic table mass is 12.011. Like, so the weighted, sum is really close to C12. And so that's what would mean that the fraction of that particular isotope must actually be then the greatest. Let's look at an example of this. So it was determined that neon has 3 isotopes. 2 were found to have masses of 19.99 AMU and 20.99 AMU with abundances of 90.92% and 0.25% respectively. Determine the mass of the third isotope. So there's our question. And so we have element neon with 3 isotopes. We find that 2 have mass of 19.99 AMUs and 20.99 AMUs. The 19.99 AMUs coordinates with our 90.92%, and the 20.99 AMUs corresponds to our 0.25%. There's two of them. We want to determine the mass of the third isotopes. And so when looking at this idea of isotopes, right, that means that we have to really look at the equation that we were just referring to. Sorry, it's at the top now. In reference to each one of the isotopes. So we could say that we have neon fraction times neon mass, and that could be for the first isotope. Then we would have that plus our neon fraction times our neon mass for the second. And then lastly, our neon fraction times the neon mass for the third isotope. And if we go to our periodic table, right, we can define the mass of our neon here to be essentially 20.179. For the purposes of our example. So that's where we get the periodic table mass. And then looking above, we have all the other pieces to plug in. We have our percentages or our fractions, and we have our masses as well. So in going up to that top purple expression, we would say that, well, we have 20.179. I'm going to leave out units just for right now, since it's a lot of numbers here going across. That's going to be equal to our first neon, which was the 19.99, times its fraction, right? So that is our isotope 1. And notice that now we're not using the percentage in terms of that number 90.92. We're using in terms of its fraction 0.9092. Then we have the second one that weighed 20.99. And so we would be at 0.25% or 0.0025. So that's our second isotope of the neon. And here is where we get at our mass. As far as the mass, and then we have our percentage, or really our fraction, which is going to come from the difference of those percentages. We have, a total of 100%. We have the 90.92% for the first isotope. We have 0.25% for the second isotope. And so that gives us 8.83% for the missing. And so that would be then our 0.0883 that we would plug in there. And so we're just rearranging this to solve for that particular mass. You know, I would just be slow and stepwise do each one of the parentheses. Sorry, that should be 0.883. And then we can solve for that mass. And we should get a value of 22.103 AMUs. So that's looking at isotopes. Isotopes, basically differences in number of neutrons within an element. So our number of protons is the same, but our number of neutrons is actually different. That then takes us to the next category, which would be ions. And so ions are basically, you know, these are formed when an element loses or gains electrons. So the element is no longer neutral. The number of protons does not equal the number of electrons. You know, if an element has more electrons than protons, then it is negatively charged, and this is known as an anion. More electrons than protons. If an element has the opposite side of the coin, or has, you know, less electrons than protons, then it is positively charged. And that's known as a cation. So less electrons than protons. So example, we could look at, you know, maybe aluminum here. Aluminum with a mass of 27 has that atomic number of 13. And now we're looking at aluminum. Again, notice that, you know, none of the first numbers change, but now we have this +3. And so there is our indication of charge. So here on the left with the aluminum, we would have 13 protons, and we would have 13 electrons. And so that's what gives rise to that notion of neutral, right, as far as the positive and the negative. On the right, we have our aluminum. It still has the same number of protons, but now is going to differ in the number of electrons. And so that gives us an overall difference of +3. right? There are 3 more protons than electrons. And since protons are positive, there's where that +3 comes into play. And you could also say that then that means there must be 3 electrons produced as well, as far as if the element lost those electrons and became +3, well, then those would be produced. Another example would be looking at maybe chlorine. Chlorine 36. Chlorine has an atomic number of 17. And we could go to chloride, where we have now a -1 charge. Right, so just like we saw above with that idea of charge, right, we're seeing it here as well. So with the chlorine, we have 17 protons basically on both sides from that atomic number. We have 17 electrons as far as the starting material is concerned, and that's what gives rise to the neutral element. But on the right side, we actually now have 18 electrons. And so that's where that now -1 charge actually comes from, that there's 1 more electron that's negative than protons. And so that means that the chlorine must be gaining an electron for that process to actually happen. So that's the idea of ions, that we have positively charged ions known as cations, which we see at the very top. We have then the opposite with anions that we see in the example below as far as being negatively charged. And so that's the idea of ions. Now, why do elements actually form these ions? It's a good question, something that we'll be coming back to. But I always like to kind of talk about this a little bit early, which is the idea of electronegativity. Electronegativity is basically the inherent desire for an element to gain electrons. Right? And this basically describes how bonding now begins to occur, or bonding between elements. Occurs basically in both, ionic and covalent motifs. So if we look at kind of a trend, and if we look at electronegativity increases up the periodic table and from left to right. So that explains why certain elements like to lose electrons or certain elements like to gain electrons. We find that elements in this general area they like to lose electrons. They're not electronegative. Well, then we find in the other side of the coin, this is being pretty rough, okay, people? With the purple, these like to gain electrons. And they are electronegative. So that kind of region that we have, kind of this area that we see off to the right side, these are electronegative elements, while a good bulk of the others tend to be more electropositive or just not electronegative. And so that starts to explain the notion then of bonding. And what is bonding? Well, bonding is basically an attractive force that locks one element next to another. And with bonding, we have really two types. We have ionic bonding. And this is basically something that results from a cation, an element that is positive or a positive ion. Connected with an anion or a negative ion. It's what they call electrostatic attraction. And eventually we'll get into talking about Coulomb's law as far as describing that. And then the other side of bonding is covalent bonding. I should say for part A here that this occurs between elements of very different electronegativities. So we see that charge aspect. With covalent bonding, this results from a sharing of electrons. Which still allows for elements to be connected. And so this basically occurs between elements of similar electronegativity. So that's the notion of isotopes, ions, And starting to put that all together as far as thinking molecules in terms of bonding, definitely light. We're going to get into all these, into much more defined detail, especially ions and ionic bonding and covalent bonding as we go.